Alright, so in this video, we're going over the conjugate root theorem and Descartes' rule of signs. Alright, here's your vocab. I copied these out of the book because I thought they were nice. It says conjugate root theorem. It says if p of x is a polynomial with rational coefficients, then irrational roots of p of x equals 0 that have the form of a plus the square root of b occur in conjugate pairs. That is, if a plus the square root of b is an irrational root and a and b are rational, then a minus b is also a root. And also, if p of x is a polynomial with real coefficients, then the complex roots of p of x equals 0 occur in conjugate pairs also. That is, if a plus bi is a complex root and a and b are real, then a minus bi is also a root. Alright, we'll get into an example of that in a minute if that's kind of confusing. The second one is Descartes' rule of signs. So it says, let p of x be a polynomial with real coefficients written in standard form. So all that means is that your exponents are in descending order. So x cubed, x squared, x, and then your constant. It says the number of positive real roots of p of x equals 0, is either equal to the number of sign changes between consecutive coefficients of p of x or less than that by an even number. Or the number of negative roots of p of x equals 0 is either equal to the number of sign changes between consecutive coefficients of p of negative x or is less than that by an even number. In both cases, count multiple roots according to the multiplicity. So those are your two vocabs, and we're going to go over those here right now. If you haven't got those written down yet, pause the video, write them down. Alright, so using the conjugate root theorem to identify roots. So we know here that the quartic polynomial p of x has the rational coefficients. It has rational coefficients. If the square root of 2 and 1 plus I are roots, what are the other two? Well, if you remember, if a plus the square root of b is a root, then a minus the square root of b is also a root. So in this case, a for the square root of 2 would be 0, so it would be 0 plus the square root of 2. So that means that a minus b, or 0 minus the square root of 2, would also be a root. Alright, that's what the rational root theorem says. If a plus the square root of b is a root, then a minus the square root of b is also a root. And here, since this is a positive square root of 2, and we have no number in front of it, it's simply 0 plus the square root of 2, making our a minus the square root of b 0 minus the square root of 2. And here, if 1 plus I is a root, then 1 minus I is also a root. So our two additional roots, to answer this question here, our two other roots are negative the square root of 2 and 1 minus I. Because, like the conjugate root theorem says, if a plus the square root of b or a plus bi is a root, then all you simply do is change the sign between them. That's all you do, is just change the sign between your terms. So from here to here, positive went to negative, same thing here, positive went to negative. If this had been a negative, it'd be a positive over here. All you do is flip the signs between them. That's it. And that's your other roots. You just flip the signs between them. Alright, so let's see how well you understood that. A cubic polynomial p of x has real coefficients. If 3 minus 2i and 5 halves are two roots of p of x equals 0, what is one additional root? So go ahead and pause this and see if we can figure that out. Alright, so we know here the 5 halves, okay, that is not in the form of a plus the square root of b or in a plus bi. It is not in one of those two forms. So therefore, this doesn't have a conjugate root. We just have to leave it as that. But if we look at this one, the 3 minus 2i, it is in the form of one of these. So our one additional root, you simply change the sign between them. So it'd be 3 plus 2i. That's it. That is your one additional root right there. Because remember, you can't do anything with that guy because he's not in one of these two forms. So this is the only one that you can get the conjugate of is the 3 minus the 2i. Anytime you have constants, because 5 over 2 is a constant, anytime you have constants, you won't have a conjugate root. You got to have a square root or the imaginary I in order to have a conjugate root. All right? Let's look at this one. Let's actually write a polynomial using this stuff. So it says, what is a third degree polynomial function y equals p of x with rational coefficients so that p of x equals 0 has roots -4. So our roots are -4 and 2i. All right, well, since we have a positive 2i, this is 0 plus 2i, so we're going to have 0 minus 2i, or just -2i. All right, or just -2i. So what we're going to have here is we're going to have x plus 4, because remember, you have to change the sign. Remember a couple lessons ago when we were writing polynomials from their roots, this is always in the form of x minus that number. So x minus -4 is x plus 4. And this will be x minus 2i and x plus 2i. All right, let's leave the x plus 4 alone for now. This here will go to x squared plus 4. Because remember, this is one of our special cases. This is a plus bi and a minus bi. It simply goes to a squared plus b squared. A being 1 and b being 2, not the I. The plus already takes into account that I times I is -1. So you just do a squared, which is, well, it's actually x, a squared plus b squared, which is the 2, so you just get x squared plus 4. All right. If you want to FOIL it out to prove that, you can just, first, outside, inside, last, and you'll get the x squared plus 4. All right, now all we have to do is multiply this across. So this gives us x cubed, and then that gives us plus 4x. This gives us plus 4x squared. Oops. And then, of course, this gives us plus 16. So let's rewrite this in standard form. So our p of x equals x cubed plus 4x squared plus 4x plus 16. So what's our final answer? Everything's positive. Looks like letter C. Letter C is our answer. All right. So when you're using conjugates to write a polynomial, don't forget that anytime you have a root that has a square root in it or a root that has an imaginary term I in it, if you're not given the root and its conjugate, you have to remember to write in its conjugate before you try to write your polynomial. So just like we did here, we're given -4 and 2i. Well, since we have 2i, we need its conjugate. So that's where the -2i comes into place. If we hadn't wrote the -2i here, we would have not have gotten a third degree polynomial. We would have only gotten a second degree. So if you're only given some of the roots like we were here, anytime you have an I, you need to get your conjugate. Anytime you have a square root, you need to get the conjugate. All right. Now let's look at Descartes' rule of signs. All right, this is that weird definition. All right, I'm sure you read it and you're like, what does that even say? That was what I thought the first time I heard it too, until I saw it explained. It's really not that bad once it's explained. All right, so what you want to do, we want to count the number of times the sign changes in here. This is positive, goes to negative, that's 1. Negative to positive, that's 1. All right, so you take your polynomial function as is, and that tells you how many positive roots you have. So our positive zeros, or positive roots, whichever way you want to call them, is going to be, we have 2 sign flips, that's 1, and that's another one, so that's 2. So we're going to have 2, or it says less than that by an even number. So what's the next even number below 2? Well, it's only 2. So we're going to have 2 or 0. All right, we're going to have 2. Let me rewrite that so it looks a little better. We're going to have 2 or 0 positive roots because it's 2 and then every number less than that by an even number. So 2, subtract 2, you got 0. You don't need to go below 0. Once you hit 0, you're finished. If this had been a 4, it'd be 4, 2, or 0. If this had been a 3, you're going to subtract 2, it'd be 3 or 1. All right? Now, for the negative roots, what you need to do is you need to look at your exponents and change the sign on your odd-powered exponents. So this is an x cubed, that's an odd-powered exponent, so it's going to be a negative x cubed. This is an even-powered, it's going to stay negative x squared. That's our constant, it's going to go to 1. Okay? So now, we count the sign flips again. Negative to negative, that's not a sign flip. Negative to positive, that's one sign flip. So we're going to have only one negative root because if we subtract 2 from it, we get negative 1. And you don't go below 0. So in this case, we're going to have 2 or 0 positive roots because we have 2 positive sign flips. Then you take your odd-powered exponents, change the signs on their coefficients, and do that for all of them, and then count again. All right, so the only sign that's going to change here is the x cubed because that's the only odd-powered exponent. It became negative, and then we only have one sign flip from there on out. So we have 2 or 0 or just one negative root. Okay, 2 or 0 or just one negative root. Now, if you looked at the graph from this, you could prove that it only has one negative root. I'm going to do a crude sketch of this graph. All right, it's going to look something like this. So as you can see, all the numbers to the left of the y-axis here are going to be negative numbers, and it does cross one time. So that confirms our one negative root. Negative just means that x equals a negative number. Positive roots, x equals a positive number. Now, this says it has 2 or 0 roots. Well, if you look, it doesn't cross the x-axis anywhere that's positive, which means we have 0 positive roots and 1 negative root. All right, because this is your possible number of roots. This doesn't tell you your actual number of roots. Well, unless you only have a 1 like this. This doesn't tell you your actual number of roots. It just tells you your possible, kind of like the rational root theorem. It gives you all the possible rational zeros. Well, this gives you the possible number of positive and negative zeros. So this could have 2 or 0, so it could cross the x-axis, the positive x-axis 2 or 0 times, and our graph confirms that it crosses 0 times. And now this tells us that it's going to cross it one time on the negative x-axis. Okay, if this had been 3 or 1, it could have bounced and crossed more. All right. So that's Descartes' rule of signs. Go ahead and try this one. It says, what does Descartes' rule of signs tell you about the real roots of that polynomial? And can you confirm real and complex roots graphically? I've kind of already answered that one for you. All right, so let's do our positive zeros. I'm going to say PR, positive roots. Well, that's positive, goes to negative, that's one sign flip. Negative to positive, that's one sign flip. Positive to negative, that's another sign flip. So we're going to have 3, because 1, 2, 3 sign flips, or 3 minus 2 is 1. So we're going to have 3 or 1 possible positive roots. Let's look at negative roots. So we need to take our odd-powered exponents and change their signs. So we're going to have 2x to the 4th, that's not going to change. X cubed, that's odd, and it's negative x cubed, so we need to go positive x cubed. 3x squared, that's even, so it's going to say 3x squared. Negative 1 doesn't have 1. So here we go. Now we got to count our sign flips. Positive to positive, that's not a flip. Not a flip. Positive, negative, that's one sign flip. So we're going to have 1, negative 0, and we're going to have either 3 or 1 positive zeros. Okay? So that answer is letter A. We're going to have 3 or 1 positives and only 1 negative. Now, can you confirm real and complex roots graphically? Yes, you can. I kind of just went over that. If you graph it, okay, however many times your graph crosses your negative x-axis is going to be your negative number of zeros. However many times your graph crosses the positive x-axis is going to be your positive number of real zeros. Now, what about these complex ones? Can you graph a complex root on an xy coordinate plane? Hopefully you said no, because you can't graph an imaginary number on a real plane. So you cannot confirm the complex roots graphically, but you can confirm the real roots graphically. Okay? All right, so that's been your conjugate root theorem and Descartes' rule of signs video. Feel free to watch this as many times as you need to. Make sure you come to class tomorrow ready to work some problems. See you tomorrow.